class. So chapter 1 is all about different graphs, equations, and inequalities. So it covers everything from radicals to quadratics, some linear equations, some inequalities. So it's a nice little grab bag of mathematics. Section 1.1 covers graphing utilities and kind of gives us an introduction to graphing equations. I'm sure this is something you guys have done before, especially in high school, but the book covers it, so I'm going to go over it again. So before we were working with just one number line, right? The real number line. Now we're switching to two. We have our x-axis and our y-axis. Okay, this is called the coordinate plane. It's also sometimes called the Cartesian plane, xy plane, rectangular coordinate system. It goes by many names, but what it means is this beautiful image right here. Our origin is the same as before, except when we just had one number line, our origin was 0. Now our origin is 0, 0, right? And that's an example of an ordered pair, which we'll talk more about in the following slides. It has 4 quadrants. We have a quadrant where everything's positive, everything's negative. Our x is negative and our y is positive, and our x is positive and our y is negative. So 4 different quadrants. It's important to note that the points on our x-axis and our y-axis don't belong to any quadrant. They are on the axes themselves. So the way I define a point on a Cartesian system is using an ordered pair. Okay, and this is a number enclosed in parentheses with a comma in between. The first number is going to be our x-coordinate, and the second number is going to be our y-coordinate. Why is that? Well, because it's alphabetical. Okay, so when we're listing ordered pairs, we're always going to want to list our x-axis and then our y-axis. So let's go ahead and look through a few examples. I kind of went over this very briefly in class, but I want to make sure we have more time now that we're on YouTube and have no time constraints. So in this case, A is 1, 2, 3, 4, 5, negative 6. That's my x-axis, my x value. And my y-axis is 1, 2, 3, 4, 5. That's where my x value of negative 6 and my y value of 5 connect. For B, I have x is a positive 1 and y is 3. Right? This is my x, this is my y. C is right on my x-axis. Because it's on my x-axis, it has a y value of 0. So my x value is 6 and my y value is 0. For D, I have an x value of negative 1 and a y value of negative 5. And if you take your fingers and see where those two intersect, that's the point, negative 1, negative 5. So that's some ordered pairs. And that's how we're going to be able to find plots on the coordinate plane. Friendly reminder that any point on the x-axis has a y-coordinate of 0, and any coordinate on the y-axis has an x-coordinate of 0. That's because on the y-axis the x value is 0, and on the x-axis the y value is 0. So the graph of an equation in two variables, x and y, is all points on the coordinate plane that satisfy that equation. So if I had, for example, I could have y equals 3x plus 4. I could have y equals x squared minus 1, right? And all points on these graphs would be said to satisfy the equation. So those are its solutions. The graph of a line is the whole solution set for an equation. In order to determine whether a point is a solution, so whether a point is on the graph, we can do that by substitution. So for example, this is supposed to be an equal sign. If I want to determine whether the following points are on the graph of my equation, so I would just substitute them in. I had to have 2 times, instead of x squared, I'd have 5 squared, minus 5 times 6, and I wonder, does that equal 20? Well, I get 2 times 5 squared, so that's 50, minus 30 is 20. This is true, right? 20 equals 20. Because I got a true statement, this is a solution, and it's a point on the graph. Let's take a look at this next example. I have 2 times negative 5 squared. Again, substituting in. minus 5 times negative 14 equals 20. 2 times negative 5 squared is still 50, but 5 times negative 14, that's going to be a positive 70, equals 20. That means 120 equals 20. Is this a true statement? No, this is false. So this point is not a solution because it does not satisfy the equation, and it wouldn't be on the graph of this. This would be a parabola. The midpoint of a line segment with endpoints x1 and y1 and x2, y2 is found using the midpoint formula. For example, I have when x is 3, y is negative 6, and when x is 6, y is negative 3. And I want to find the midpoint between those two. So what I'm going to go ahead and do is I'm going to say, my midpoint. Now over here it uses a lowercase m, but I'm not going to use a lowercase m, right? That's because a lowercase m typically denotes the slope of a line, right? A 1 degree equation, first degree equation. So let's denote this with a capital M. So I'm going to go ahead and I'm going to say capital M equals my x values, and it doesn't matter which is x1 and which is x2. I just have to add my x values. 3 plus 6 divided by 2. And I have to add my y values. Negative 6 plus 3 divided by 2. That means my midpoint for this first example is going to be 9 halves, negative 3 halves. And that's okay, right? I can graph rational numbers on our number line. Remember, our number line is the real number line, so it has all rational numbers, all irrational numbers. We can graph them all. Let's take a look at this next example. I have the midpoint is my x values, so I'm going to take negative 8 plus negative 2 divided by 2, and 4 plus negative 6 divided by 2. I'm going to simplify that. Negative 8 and negative 2 is negative 10 divided by 2. 4 plus a negative 6 is negative 2 divided by 2. So my midpoint is negative 5, negative 1. That's going to be the midpoint between these two. One thing it talks about in the section 1.1 and 1.2 worksheet that I posted, but that I didn't cover explicitly in the PowerPoint, was the distance formula. So I'm going to go ahead and go over that now. So the distance formula is used to calculate the distance between 2 points on a number line. So let's go ahead and make a really rudimentary coordinate plane. And go ahead and plot 2 points. I'm going to plot when x is 1, y is 2. And when x is negative 4, y is 0. And I want to calculate the distance between these 2 points. Now I'm not interested in the midpoint, I'm interested in the distance. So the distance is going to be the square root of x2 minus x1 squared plus the square root of y2 minus y1 squared. So let's go ahead and solve this. I'm going to let negative 4 be my x1 and 0 be my y1, and x2 be 1 and y2 be 2. Now it doesn't matter, again, which is my x1 and which is my x2, as long as you're consistent that your x2 is always paired with your y2. So I'm going to take the square root of 1 minus negative 4, I'm substituting in my x2 and my x1, squared, plus y squared, which is 0, y2, which is 2, so you have to be consistent. Make sure you're consistent. So now I take 2 minus 0 squared. So I have the distance is the square root of 1 minus a negative 4, that's 5 squared, plus 2 minus 0 squared, that's 2 squared. So distance is the square root of 25 plus 4. So distance is the square root of 29. Now, 29 is a prime number. I can't pull any squares out of this, so this is fully simplified. If you wanted to know closer what it was, you could plug it into your calculator. Again, this is an irrational number. And if I took the square root of 29, I would get 5.385. And this is an irrational number, so I'm rounding, right? I wouldn't ever go more than 3 decimal places. So that's the distance formula, in case you needed a little refresher. So we can use graphing utilities to visualize equations, right? And we can graph by plotting points, or we could graph by entering an equation that we have solved for y. So some most common graphing utilities are going to be graphing calculators. I think most of you already have one of those from high school. If you don't, I really like Desmos. It's a free phone app. You cannot use it on an exam, but it never hurts. And last but not least, you can use this NumWorks calculator simulator. It's kind of slow, but it does simulate a graphing calculator. I think your best bet would be to get a graphing calculator, or remember you can check them out from Pius if you do not want to purchase one. So when we're graphing our equations, in order to solve them, we want to look for some very specific things that are special to our graph. And those are going to be our x-intercepts and our y-intercepts. So the intercept of a straight line, right, is only going to have one x-intercept at most and one y-intercept at most. But it's important to note that if I was graphing, say, let's change colors. If I was graphing a quadratic equation, right, something of the form y equals ax squared plus bx plus c, it could have two x-intercepts, okay? So our y-intercepts are of the form when x is 0, y is something, like b, and our x-intercepts are when y is 0, x is something. So I'm going to have like a2 and a1, and I'm just making up variables with numbers to label the fact that I have multiple intercepts. So I can approximate our intercepts using a graphing utility. So there's a 0 feature in graphing calculators that would let you look at the graphs. I have attached a link to a video on how to use the 0 function. I really like using the Desmos graphing calculator, and here's why. So let's find the 0 of y equals x cubed plus 4. So I'm going to click on this calculator and hope it's still recording. Ah, it is. Wow, life's great. So I'm going to type in y equals x cubed plus 4. Very slowly. Well, I don't need 3 equal signs now, do I? X to the 4th plus 3. Sorry, it was x cubed, wasn't it? That'd be way more interesting. X cubed plus 4. So a few things. I hope you can see how as I'm altering the equation, the graph is changing. Also, if I click on my intercepts, it's going to give me the points. Oops. It'll tell me the points directly. I can't move the graph itself, but I can click on the graph and find any point on the graph. So that's pretty cool. And like I said, I can also compare, like, okay, here's x cubed plus 4. What if I wanted to compare that to y equals x to the 3rd plus 4. How does that change the graph? I can do so. Oops, sorry. I meant to put that cube on the outside. That's not different, is it? So we can see what happened here, right? If I add 4 outside, it shifts my graph up 4. If I move it, put it inside, it shifts my graph to the left 4. And you can always compare it to the basic cubic, which is x cube to see how your graph was shifted. So that's why I would recommend using Desmos.